Dushan.
Thank you very much, Bernardo. Thank you very much, Marielle. Bonjour, mesdames et messieurs. I apologize that je ne parle pas français, but I will try to, and I really apologize. My father told me you will never be civilized unless you speak French, and obviously I'm not civilized. But so it's a great pleasure to be here. I met Ariel a few years back, and they said they are starting a center, and says, well, good, we have a center for 30 years. So it's a different center, and I will talk about that, but I'm also very pleased to be here to share with you what we did in aerospace, because I did work in aerospace power electronics technologies for quite a few years, and with many people that in many companies that are represented here. And Regis is here, or he left there. And from Suffern and many others supported our work for many years. So it's a great both pleasure and honor here to be and share with you what we have and see how we can collaborate in future. So with that, let me start on our where we are. And we are from CPES, Center for Power Electronic Systems. We do not have any writer who was flying airplanes and fighting in a war and writing novels for children, but so that's a nice name that you came up with. I like it. And we are in east part of United States, close to Washington, D.C., in a small town of Blacksburg, which has about 50,000 people, and out of these 50,000, 30,000 are students. So the other 20,000 give the food or lectures to the students, and that's all there is there. So typical university town in Blacksburg, some pictures of university campus over there. In that university, as I said, over 30,000 students, and 80% of them are undergraduate, 20 of them are PhDs or senior master student, and about 3,000 different types of professors or instructors, so every 10 students, one professor. An interesting thing here is that although this is a state university, big amount of funding comes from different areas, less than about 20% comes from state. And then a big part comes actually money we take from students. So our students take studies very seriously because they pay for it. So if they don't want to study, they just don't study for a year, go do something, and then come back and pay again. And there is a large amount of that is coming from research. We have a lot of things, areas from science, liberal arts, agriculture, engineering, business, but we do not have medicine and we don't have a law school. So then we would be fully complete university. This way is, these two are missing. And I am in a college of engineering, and that college of engineering has many, many different departments. Some are traditional, like mechanical, and whatever, the civil engineering, but then some others are more interesting in new, like biological systems engineering, kind of crossing the disciplines of engineering. And the Center for Power Electronic Systems is in the basement of this building. Whole basement belongs to us, and that's within electrical engineering. Brief history of our center started in late 70s with one professor, Fred Lee, and one graduate student, and that was not me. And then developed over time. I joined there. I was actually a graduate student there from 82 to 86. Then I left. And then they succeeded much faster when I left. But in the 90s, I came back. Actually, Fred came after me and brought me back. At that time, we were Virginia Power Electronics Center, and as you see, this is number of people working in that center has kept on growing very fast. And in 1998, we became a National Science Foundation Engineering Research Center, and I say a few more words about that. National Science Foundation is equivalent to CNRS here. And then we were 10 years that, and then after that, we're back to normal where we are now. Roughly, our model that works, there are 5 professors there, and we all are paid by university. We work for university. But actually, we teach a few courses. Most of the rest of the time, we run out the world and ask for money. Can you give us a little bit of money? So when we get some money, then we, 5 of us, pay about 50 PhD students and about 10 staff that work with us, and all the research expenditures to do and educate these students. So that's kind of the model that we work. This National Science Foundation Center that we got, and we started in '95, asking this question in order to get center, what is power electronics? And power electronics has 2 words, power and electronics, right? So it could be like electronics, which has a Moore's law, which every year and a half, it's half the price, or for the same price, 2 times better performance. Or it could be like power, where, you know, when we were electrifying the world, then it was changing 5% every year and a half, not 50. And since then, actually, it didn't change much. So is power electronics more like power or more like electronics? And says we'll make it more like electronics. And then our paradigm at that time was that all the secret is in integration. If we come with integrated power electronics like integrated circuits, we'll solve everything. Good, we got money, and we got money to solve that in 10 years, and we didn't solve it. But I think we made some progress. So the idea was really to combine more interdisciplinary. So traditionally, power electronics was depending on devices, semiconductors mostly, and controls, and then application areas. One was motor drives, the other was power supplies. That was the definition for power electronics. And what we said, that's not enough. We need to know how to put all these things together. To be packaging is not just something for industry to do at the end, but to do a science of packaging, science of materials tied all together, and also system level science. How do you build power systems from power electronics? So this is what we did propose and got the funding from CNRS of United States, and for 10 years. And we had 5 universities there. We were lead university, Wisconsin-Madison, as most of you know, is the famous university in motor drives, electric machines. And then Rensselaer Polytechnic had excellent device people and had a fab, so they could make, again, devices and silicon carbide devices in university environment. Another nice thing was that already at that time, Virginia Tech, University of Wisconsin-Madison had a consortium of about 40 companies. When we joined, we had 80 companies together. So that was from the beginning, we had that support. And then we had 2 smaller institutions, University of Puerto Rico, Mayagüez, some very good researchers, but also very convenient for our January meetings. We always went to Puerto Rico. And then North Carolina was a neighboring school, predominantly black school. Okay, so this is the most expensive slide that exists in the world, probably. We got about $40 million, and this one summarized $40 million spent in 10 years is in one slide. Okay, very expensive. So we started in '98 getting some benchmarks. What was the state of the art of that from semiconductor, passive components, and then 2 types of applications, motor drives and power supplies. And then starting doing research on fundamental sciences and new devices, integrating them into new packages, going without wire bonds and coming up with new interconnect techniques, adding more and more into the modules to achieve higher levels of integration, even proposing integrating capacitors, inductors, transformers into original but complete electromagnetic structure, which provides whatever needs to be provided, attenuation of some frequencies, amplification of the other frequencies, and so forth, not separate things. And both theoretical and practically how you put everything together so that this kind of a power supply, which has about 100 components, could be built from 10 or 15 components with high levels of integration. And then continued looking still on the basic things, kind of die attach, how you put the things together on devices. First 600 volt gallium nitride MOSFET ever published was part of the research that was done in that center. And then started looking how this can impact systems. Like, can we have a motor, power electronics integrated with electrical machines, or even with the phase of the electrical machine, and then just put the phase with its own power electronics around and get the motor. Something similar that the project you're still exploring because we didn't solve it. And Also integrating for lighting, for at that time not LEDs but fluorescents and filters and so forth. And then how that impacts larger systems like data and communications, ships and airplanes. And that's why I'm here, because of this last application. So that was 10 years excellent experience and many new things that brought out, and all of us learned a lot from that. So today, this was all 5 universities, about 200 graduate students, and about 220 professors working over 10 years. What I'm now, this is what we do at Virginia Tech in that Blacksburg in CPES now. After that is a long time gone. So we still do a lot of areas from kind of science or fundamental level of research. Components, we do not have fab or devices, so most of the components, we destroy them. I mean, we get the samples from everybody else, try to characterize them similar like what you're doing here, and learn from that and tell other people what is good, what is bad, and how they could be used and cannot be. Still very strong on integration and packaging, how putting things together. EMI came out to be extremely important, so we are paying that to that. And then modeling control and power conversion topology circuits, this is standard power electronics, still do a lot of that. From applications, we don't do everything, but we do quite a few different things. Something that Fred Lee started 40 years ago was how to supply power for computers and telecommunications, and still we are a leader in that in the whole world in the research and applications. But it's a wide power range from, you know, watts in cell phones to the kilowatts in data centers. And then another very strong, which is over 30 years experience, is for vehicles, for transportation. And most of it is for the airspace and ships, but although we do have support for the trains and cars as well. And the last one, which is probably the last 10 or more years, is going even much higher power for the grid applications, how we change the electrical power systems for humankind. Interesting thing about research group, not that we have a quite broad area in technologies, but also in application powers. We do work on applications from watts to megawatts. So how do we fund that? We have now, this is current consortium of 84 companies. And they're structured in 4 different types of layers. The key ones is associate layers. They have free access to our publications, conferences, other information. They have representation on our industry advisory board. If they want to send engineers to spend time with us, first they have to be at least a that level member. They also help we help them get internships from our students. They have discounts on short courses and other services. That is for $15,000 a year a gift. Okay? Affiliate members is the ones that give us things in kind, mostly software companies, or give us capacitors or things like that, or Tektronix gives us a lot of oscilloscopes, not free, but a big reduction in price. And then we give them similar benefits like this, but slightly less. Principal members, $30,000 a year. This is an interesting one. They have the same rights as those below. They have each one seat on our industry advisory board. And then this is an important piece. They have preferential access to intellectual property, which means that these companies, including the ones above that, have a non-exclusive, royalty-free access to all the patents and copyrights that comes from the research funded by the consortium. If I have a contract with Suffern, well, that's only Suffern. But if I do research and graduate student on something that's not on the Suffern contract, then that is shared with all of these companies non-exclusively, and they don't have to pay anything additionally. They just pay their membership fee, and they get that right for that year in which this was disclosed. Now, we don't patent everything, we disclose everything, but these companies meet every month or every other month, and there are 2 or 3 patent disclosures, and then they hear and listen whether that should be patented or not, and then they vote. Now, all of them have a right to vote, all of the 2 top principal and principal plus members. Out of whatever, 50 of them, probably 5 of them call. Not always the same 5, but depends who. But whoever calls, they vote, and whatever they decide, that is patented to be shared by all of them. So that's an interesting model that we developed in our university, and that our university accepted. That was a big struggle. They all want to get billions and get rich, and says, no, no, no. We give it free because they support us, but they support us for 30 years. That's not free. Many PhDs came out of that support. So, okay, we were able to do that. And then the Principal Plus have the same rights, but they also participate in specific broad research topics, and I will tell them a little bit about them next. And you will see, well, I will have a slide that they're all from all over the world. So those specific, the top guys that give us $50,000 a year, they can choose one of the 3 projects. One of the projects is a high-density integration, and this is working on materials, characterization of devices, integrating modules, integrating converters, a very wide power range from watts to megawatts, very high frequency range. If we are in a watts, we're trying to switch at tens of megahertz, so something that nobody will do, but we want to see if it can be done. And then at megawatts, we're trying to push hundreds of kilohertz, and then what's the benefit, what's the penalty, also working at high temperature. We have about 15 companies there, like Suffern being a French company, Alstom being a French company. And most of those were actually founding companies. When we started this NSF program, they joined us and have been with us since that time. The interesting thing here that practically all of them, except some device companies, materials, Dowa is ceramics, Sumitomo is silicon carbide devices and materials, practically all of the rest is in transportation. And that's something I mentioned also at the conference, transportation. This makes sense because in transportation, if you can reduce the size and weight, then both airplanes and cars and ships can pay much more because they can use the savings to charge more passengers, transport more weight, or go further with the fuel. So this is where the benefits of more expensive but smaller and lighter and more efficient can be paid by system benefits. And that's why they are here. There are no ones that do for industrial applications. They're not a single company here for industrial applications. So these give us $50,000 a year. Now, interesting, this 50,000 times 15, 250,000, whatever, no, 500, 750,000. What that pays is about 10 graduate students. Those 10 graduate students work on one coordinated project. All 5 professors actually are involved in this one. And we choose topics to work. And then every 3 months we have quarterly review where all these companies either come in person. This is when twice a year we have in person. Once they come to Blacksburg, another one we go to some big conference somewhere else. And they come and listen there or can join through WebEx. And this is like a 6-hour event where our students present, all of them, their progress. And then we have at the beginning half-an-hour discussion, at the end half-an-hour discussion, what's next. And that's how we define the topics. And this is an example of one of the reviews. I think a year ago, students go and present what they were doing, EMI, integration, double pulse extraction, and so forth. Again, models and characterization. And these are the topics that a year ago were the ones that were students involved. So as I mentioned, some materials, magnetic materials, also reliability modeling and design for thermal stresses, advanced magnetics, active device characterization, many different low voltage, even high voltage 10 kilovolt devices, and then integration of the modules at lower and higher voltages, and then finally system level things. So that's kind of scope. And during this discussion with industry, modify something. But it's interesting, most of these companies are competitors to each other. And we don't take advice from that one by one. They have to sit in the same room and tell us what they want to do. So this is difficult to manage, but actually it works relatively well because all of them then look for the common problems which are far future. And for them and for us. And that's the right thing for PhD students to do anyway. Obviously, if they are not happy, they will leave. Because membership is always for 1 year. So they pay this year, and if they don't like, if we don't hear what they want, they just don't pay next year. And some others join. So this is how this works, and it has worked for us relatively well over the last 20 years. Okay, another consortium is power management. This is more toward the previous, more fundamental technologies and science, where this is more applications. I'm not going to go details, but applications for the IT industry, telecommunications, and two types of companies. Some of them are just plain semiconductor companies, and the other one are power supply companies that use semiconductors to make power supplies. And again, these are all competing against each other. These are all competing against each other. That's the oldest consortium. This one has almost 30 years now. The previous one is 15 years. Okay, examples of the latest thing funded by consortium latest. This is already 5 years old. When new GaN devices appeared from EPC, then we immediately tried to build a converter with them, and a simple buck converter, 25 watts output, but at 1 volt. So this is quite a few amperes, so it's not that easy to make it efficient. And then actually we built it and compared it to this commercial silicon solution. It was all bad. So why do you use GaN? Because the efficiency is worse than silicon. But when you read the data sheet, it should be much better. So obviously we don't know how to use it, so we didn't. So we started looking and found that much of the switching losses, switching at 1 megahertz, were such that it was because of the large inductances. And then we need to minimize that, reduce that by half, change one of the devices from the smaller to bigger one, and immediately got huge improvement in efficiency. And then further did it on ceramic for better thermal management, reduced the loop again a half, and another one reduced another half, and then now we're going to 90%. Okay, this is something silicon couldn't do. This is an easy thing. This is about 3 graduate students working for 3 years, and you move from here to here. So yes, and that means about $300,000 a year. So it's a $1 million project for 3 years, not per year, but $300,000 per year. So to get those results, it's a lot of patience, a lot of tries. Here are just the things that worked, typical results. There are hundreds of things that didn't work. But that's what research is. We went even further, achieving much higher power densities. This is like hundreds, thousands of watts per cubic inch. So watt is watt, and cubic inch is what 6 times 2, about 12, divide by 10. So let's say 100 watts per cubic, 10,000 watts per cubic centimeter. 10 kilowatts. This is, or 10 kilowatts per liter at 40 amps. This is totally integrated transformers inside. I will show something later for airspace that we're doing for Suffern. And the last third consortium is the high power applications for renewable energies in a grid, where we look at the DC and AC microgrid, modular multi-level converters, and the power converters for these applications. This is starting at 4,000 volts up and at 1 megawatt up. This one has a fewer companies, but also, one thing that's interesting, in that range, we also have a lot of funding and special research contracts from, let's say, US government, US Navy, in this case. And this was, can you come up with modular converters so you achieve high power, not just making bigger devices, but stacking a lot of together. So we chose that, started this a few years back, what they call it power electronics building block, where you can a modular structure control, very high power density, and then, since again, solve the problems with parasitic components, scalable voltage and current. We chose an H bridge with some EMI filtering both on a AC side and a DC side. So this would be that H bridge, and one H bridge will give some voltage and current rating, and then you can increase the voltage rating by putting those in series, or if you increase current rating by putting them in parallel, and you can go or have a 3-phase converter. What we did at the end, this is the converter that was built, and this is about 30 by 30 centimeters, and this is about 12 centimeters height. And actually, there are 2 silicon carbide modules. These are 400 amps, 1.2 kilovolt MOSFETs modules, silicon carbide. There's one here, the one at the bottom, and actually the top surface is a heatsink and the bottom surface is a heatsink. So that's why they're back to each other, form the H bridge. There is a controller there with the several processors, local power supply, which takes the power locally from the local bus. so there is no common mode propagation. There is some filtering on the DC side, AC side, integrated laminated bus, and so forth. So we achieved a 100 kilowatt converter in that volume, switching at 100 kilohertz and a 98% efficiency with a power density of 6.6 kilowatt per liter. And this is switching from, let's say, this example test from 200 to 300 amperes. And the voltage here is, this is 1 kilovolt test. So this is 1 kilovolt DC bus. Okay. In fully modular control, these talks to anybody, all these fibers here are internal. Only one fiber goes out and one fiber comes in to talk to anyone else. Okay, a fully programmable, configurable online with diagnostics and so forth. Some of these are dreams. This is built, but we're now going further and seeing how to do that in a system. An interesting thing here for silicon carbide, what we did, we built a Rogowski coil for current sensing. So actually in this printed circuit board, which is a gate driver, it extends above the device, and then there is a Rogowski coil built inside the PCB. So when you screw the bus on the top, that measures the current through the screw and resets it. And what it shows here, actually you can't see it, but there is an orange underneath this yellow. Orange is measured by this Rogowski coil. No, that's actually measured by Tektronix probe on a scope, and then the sensor is the yellow one. And it matches very, very well, not in the values, but also in the frequencies. This has a multi-megahertz bandwidth. And the cost is actually not even twice what a gate driver alone would be. Now put also intelligence on a gate driver with FPGAs and so forth. We're trying to sense the voltage as well as high frequency voltage. And again, talking only through the optics because of common mode noise in such examples. So to summarize this, okay, one more thing here. This is government sponsored. Federal government, no IP rights, they don't care about that. So also all the IP that comes from this we give to our principal members for free because they are members. If they were members that year when this was patented. So they get also, well, sometimes government has a commercial entity as a part of the contract and there may be some additional rules. But if this is purely government funding like this one was, it's free, we can do it whatever we want. So we give our members that one. Okay, so as I said, members must be always on the coast, so it's east or west coast of the United States or east or west coast of the Eurasia. Yes, we're well distributed. A lot of companies from North America, but quite a few Asia and Europe. And that's our consortium. And with that, this is the principal funding, the brown, when we started in mid-2000s, and it grew substantially. So right now, our main funding from the consortium comes of more than $2 million. And then we have something from the principal members and those associate members. And this is what funds half of our research. Half of our research is from this consortium that I described. Another 2.2 million, or another half, is from the contracts. One contract could be like the one I described with the government, Navy, but the contracts also with the companies. For example, Suffern is a member of consortium, but is also giving us a contract every year for the last 10 years. So they take both sides of what we can do. On contracts, obviously, the IP and everything else is how we agree. The contract says deliver this by that time and this by that time and then this and that and so forth. And of the contracts, half are industry and half are federal government. What we produce a lot of graduates, a lot of papers, and some patents, and that's our production. So before going on airspace, maybe I'll stop here for briefly if there are any questions of this structure and how we operate. And then I have to say, well, similar amount of time. About some of the research examples so recent on power electronics. So any questions here before I proceed? You have to talk here.
Okay. So how long do the member stay with you? Is it really long lasting, or do you have partner who come for 1 year and then go away?
Both. We have companies come for a year and then go away. And obviously, we will not feel good if we said we didn't do it well. We says they made a mistake. But yes, we do have that occasionally. Most of them stay for extended periods of time. Let's say 5 years would be normal. And then actually many of them stay, many companies work with us for 30 years. So it depends on interest and shifting, but also depends on management structures and how they do. The thing that works relatively well here, I think this 50,000 euros or dollars is not such a big amount of money for companies. And just being part of the club that's doing some good work for them, I think most of them is important. Actually for them, one thing is technologies we do, but probably for at least half of them, they're members in order to get our students. They are there to be in touch with students, to know which one, and to be first ones to offer to come. So they are really there for recruiting, and when they pay their recruiters to go out to recruit, it's actually more expensive than this. So they find a good value for this. But most of the companies stayed for a longer time, so 5 or more years. Now we lose some companies like Infineon comes and buys Cree and buys international rectifiers, so now we had 3, now we have only 1. So, okay, we hope somebody will split, so we can get some more. But we just lost 2 members. And Infineon didn't triple their membership. They said they're still single member. But some companies, GE has double, Delta has triple membership, so some actually to be members of all 3 consortia I mentioned. So if you want to be member of all 3, you get intellectual property from all of them. But in order to be participating quarter reviews and saying what should be done next, you have to be member of, you have to pick one. And if you want to be on all 3, you have to pay, give us 3 times 50,000, which several companies did. Huawei is that, so. Anything else?
And sponsored research is split between governmental and industry sponsored?
What is it? The government split? Sponsored research, yes, it's about half and half. About half of this, a little bit over 1 million is government, another is contracts, companies. All contracts, yes, but government or companies, yes. Where our contracts for government, at least in our center, but it's generally different in the United States, they are contracts which have a technical topic. They're not funding PhD students. So it's similar company or government. They says, this is the theme, this is what you should do in this many time, and that these are the milestones you should achieve, and this is what you deliver, and that's it. And they don't care whether I have 1 student or 3 or 5, it's fixed cost, and I do it. And the companies are about the same. It's very similar. The only difference is companies, when they commit on a contract, that's it, and if I don't spend all the money, I can save it and pay my trip to France. But for the government, I cannot do that. Whatever I don't use, they take it back next month. So, but that's government. But yes, it's a 50-50. So we are unusual a group. This is university, and we do believe that we do scientific research. But 3/4 of our funding comes from industry. Half from consortium, 1/4 from contracts, and only 1/4 from government. When we had NSF Center, then half was coming from government. Okay.
One additional question. Do you have any figures about the use of IP by your industrial members?
That's an excellent question, and we really would love to have it. But this is the secret of our success, that we don't know it. Because that's why companies like it. Because they have automatic, non-exclusive, royalty-free right by being a member. So the moment they sign a contest to be a member for that year, they have that right. That means they don't have to tell me or anybody in the room which IP they're using in what product. And they think that's beneficial for them. That's their competitive advantage. They will use it however they want to use it. Where the only thing we promise, we will not sue them if we discover they're using our product. And we never sued anybody, so they trust us. So that's how that works. So in some cases we know because somebody told us and so forth, but really we believe that there is much greater use that we specifically know. And some products, you know, like one thing that's multi-phase buck converter that every PC in the world is using that converter. Every. Okay, that was our patent. Now it's expired, but 20-something years ago. So, so this was a big impact. But again, we figured it out when we saw that everybody, every single one has that, and we were the first to publish and we were the first to patent. So that one we knew. And so some of those we knew, but I'm sure there's many more which we just don't. Like Semicron was for many years a member there, not now, and they were criticizing everything we did on packaging. And then they come with new scheme module and this and this. This is direct copies of what we did. But they were members, so everything's fine. They were members when we did those patents. So, okay, anything else?
One question. IMEC?
Yes.
Is it the same model that they use because they are not as old as you, I think?
IMEC is a consortium of semiconductor manufacturers here in Netherlands, seated, but it's European. And a similar model, although it's driven differently. ECPE, I don't know how many of you know, European Center for Power Electronics, has very similar models, but all of those are driven differently. IMEC is kind of a little bit industry, a little bit government, and standalone organization. They have members from both universities and industry, but they're not university organization. ECPE is completely separate from any institute. It's just a managing organization funded by industry as a separate foundation, and then they have excellence, centers of excellence. One of you, I just learned that you became one of the centers of excellence where the research is going. Very similar model for the IP. But there is the details. We are single university and a whole bunch of companies just supporting our one university, which is good and bad. We love it because we take it all. But also, you know, from the long term, if I leave or die, then who knows, this disappears. There is not institutional. The other two have better institutional longevity. So there are similarities and differences. I think both IMPEC and ECPE copied a lot of ideas that we were trying to do first. But it's good. I think it's very nice. Okay, so let's go a little bit more on technology. Aerospace actually started early. Fred Lee, he did his PhD on a funded project by NASA, and that was 72, okay? So this was way in the last century. Since then, we have always had, so that started with the obviously government funded, but we had since then a lot of projects funded by Force, Navy, and industry continuously. There was one by Air Force when they were dreaming about, they called it 21st century airlifters, big airplanes. And actually many of the studies that came from the Office of Scientific Research from US were later used both by 380 and 787. Architectural ideas and the approach to doing the more electric aircraft was actually developed. Both MEA concept and the architecture came from, not from us, came from Air Force Office of Scientific Research. We're just one of the subcontractors that provided some ideas that came from that. But then interesting, when we published some of these results, first company that gave us money was actually Tallis. And so we had the funding from them to do simulation of parts of that system because they were trying to compete and get a project from Boeing, but they didn't have any simulation experience, so they came to us. We did all the simulations, they got the bid, and we were very favored by Tallis. But then Boeing says, well, I'm paying Tallis to give money to you, I'll give money to you now directly, so that's how we got really involved. By the way, there is even earlier history. My first aerospace project came from the company called Artus. And I'll talk about that. I'll mention it again on one of the next slides. So anyway, at that time, we did a lot of simulation modeling of power systems, so more electric aircraft, as well as developing hardware for Tallis, what we called those NSF idea of integration. It's not integrated circuit, we call it integrated power electronics module. And then Tallis saying, okay, can you develop for us something for airspace? And we call it TalliPEM, not IPEM, but TalliPEM. Okay, so we developed TalliPEM for them. I don't think they're using it, but anyway, there was a lot of technologies there for reliability and high power density. And we also developed a controller for fully digital generator control unit and so forth. This is about 20 years ago. But when the Widebandgap semiconductors came around 15 years ago, then everybody wanted us, and we wanted to see how they will change the world. So we first started getting any devices we could from anybody, Cree, GE, Genesys, Chrome, Infineon, Semi-South that doesn't exist anymore, and so forth. And destroying them and characterizing them, pushing them to work at high temperatures, seeing how low the conduction losses are, how low the switching losses are, how they depend on temperatures and different parameters. Very similar things that you're doing. We have been doing this from the beginning, from the first possible device we could get samples, and got very good results and promising things that you all know, that these devices are much better than silicon MOSFETs in a sense of loss, especially at higher voltages, and then much better in the switching losses than silicon IGBTs. So they take silicon, you have to choose this or that and sacrifice something else, and these actually can combine that and then provide a high temperature operation which silicon cannot. So there are clear advantages of one would do that, and there are probably a lot of disadvantages we don't yet know, but those that build airplanes will learn when the airplanes start burning or falling down. But that's in the future. One of the first ones to support us were GE and Boeing, and this is just one of the examples to use silicon carbide, what they call AFE, active front-end converter, where we use the three-phase inverters with some original current sharing structure here for the filtering. And then we use the JFETs at that time, the only active switches that were available more than 10 years ago, almost 15 years ago. And then they wanted to work at 250 degrees C. Devices could work, but there was no package that anybody would even attempt, so we were the first ones to do that. So we built a package with original choice of materials and structures and interconnects, and were able to actually make the module and then build this is a half bridge, and then 3 of those forms a 3-phase bridge, another 3-phase bridge, and they work in interleaved mode. And we built a complete demonstrator, converter, full control. This is controller, this is the gate drives, this is EMI filter here, and current sharing inductors, and had it working. 15 kilowatts, 6.3 kilowatts per liter, which was a record at that time. This was, I think here, just the devices work on high temperature, everything else is low temperature. So here the only thing is that heatsink could be about 5 times smaller, almost 8 times smaller, because of the large temperature gradient. Ambient temperature is 70 degrees C, now your junction is 250, there is a lot of difference, so you can have small heat sinks. Okay, so good, we solved the packaging, we did it, works well. So this is the ceramic on which we mount all these devices, and then using airspace, we did some cycling every hour, go from minus 50 degrees C to 200 degrees C, and then minus 50 to 200, minus 50 to 200, and after 20 cycles it falls apart. So it's not very reliable. In a flight you may have 5 to 10 cycles, so that means for safety every flight you will have to change the converter. So that's not very good. Maintenance. And then we did a lot of physical causes of failure studies and why did it fail, where and how. Some of the things were well known, but we learned a lot, which other people already knew. And then start thinking. So one of the things is, if you have ceramic and copper of this, there is so much stress and because of the strain of different thermal expansion coefficients of ceramic and copper, that it starts cracking. But people have seen that it always cracks from the edge, so if you make the edge kind of stepped, then those forces could be reduced and it could last longer. So with that one is go from 20 to 100. Wow. Now 4 flights or maybe 3 flights you have to change. But then we started, somebody says you need to seal it because there is some moisture coming in or some other contamination. We tried, it didn't help much. Actually, it was not a contamination. This is again stress relief. If you have stepped and choose some specific organic encapsulants If you don't step and just have that, it's improving about 10 times, but not really enough. It was interesting that you have to do both stepping and grading here and some special encapsulants, and then you can go into thousands. Okay, this is still not very good. They would like 5,000 to 10,000 cycles, but this is on the way to get there. So we do, we go and build a converter, and then we go back to the science to see whether it should work, and we continuously do that. So now, with the stepping and this, we were able to achieve these thousands of cycles, and this is what we now use for high temperature. So this was an interesting one funded by Rolls-Royce as a separate contract, who also at that time was a member for many years. And they wanted to do a starter generator, again, just a three-phase converter from starter generator to 540-volt bus. 250 kilowatt was goal to work at 250 degrees centigrade. Okay, can you do it? But now everything sits in FEDEC environment inside the jet engine nacelle. Okay, so again, you have to come up with your own package with the low inductances. You have to build everything. You have to build enough of them so that you can build a converter, and then some typical ones work, but all the others blew up. But at the end, we got a 50 kilowatt system working and demonstrating. Again, this is rare for university that you go from device packaging all the way to the converter that's then cooked at 250 degrees C and see how it fails. So Suffern work, okay, 787 is more electric, replaces pneumatics, replaces this, everything is lighter. They build it, nothing is lighter. They forgot to count EMI filters. So when you add all the EMI filters to match all the power quality and EMI specifications, it's just the same weight as pneumatics. They were not happy, but anyway, we learned something, so it flies. But not as many passengers and cargo as they hoped. So anyway, so many of this was a project funded by Suffern, but many of the companies really then focused around the world on reducing the EMI so that you don't have to have that many filters. And then a big part of that was even knowledge how to model an EMI. This is a program funded by Suffern. This is just a commercial motor drive, put it in there with the standardized test fixture. Where did it come from? Well, it came from 4 years of research funded by Suffern, how to do that. So when you do this and you can change different impedances here, you can measure the noise at input and output of whatever converter you can do. And then you can actually measure that noise. And based on that, you can develop a model, which is linear model or semi-linear model, that models the whole drive as a source of noise, both an input, but takes into account the impedances that could be connected on each side. So you decouple that. And then what you're able to do is obviously predict back the noise, that's the black, predicts the yellow, the green one, which was measured, if you do it under the same condition as before. But then if you change the length of the cable, both input and output EMI changes, and we can predict it very well. If you change a LISM, well, nobody changes LISM, but if you change the source, you can also have huge changes, very well predicted. You can change a filter. This is the key. Now, when I do simulation of a filter and I say this filter will filter this well, I put it in and it works. And you see I put a filter only on the input, but actually changes both input and output. Okay, I put it in output, it changes both input and output. This was not possible before with the models that existed. This was about 10 years when we got those results initially. Now there's quite a bit transferred here. So that's the work we did for the sake of speed. Another project by Suffern where we were looking for active filters to reduce the size. So you can inject here the counter. You measure kind of what noise there is, and you inject something opposite to cancel part of it at low frequencies. And this one shows that you can do it. At high frequencies, you still use the passive filter, but at low frequencies, you use the active filter and use something that's very small like this that replaces 80 millihenries choke, which is 1 kilogram choke, much, much bigger. With Suffern, as I keep mentioning, quite a lot of support on filter design, using silicon carbide inverters and seeing what it does to EMI and how to predict it in the same modeling structure. Lately, also this integration that I was mentioning, where this was just finished, and this was done by our student working in Lyon here in a lab with Ampere together. So she came up with the ideas, but actually did the manufacturing here in Lyon. And then we don't manufacture euros, but the whole converter of 2 watts is the same size as a euro and the same thickness, about twice the thickness. That includes the transformer with very, very low, this is for gate drives, very low primary to secondary capacitance of about 1.5 picofarads. This is a low power 2 watts. So again, using the things that we know how to do, power supplies for cell phones, how you use that for airspace environments, for the gate drives, for GaN converters using, and so forth and so forth. Okay, this is a TRU. I'll come back to R2s. So normal, all of you know what TRU is, right? Transformer rectifier unit comes from fixed voltage and frequency here to 28 volts for avionics. And the first one I did was by Artus. And then they delivered it to Boeing, and Boeing put it on V-22. And then Boeing went around that they have electronic TRU, and the first one was developed by us for R2s, and this was unbelievable. This is the only time when something from idea on soft switching went from the paper published to thing flying in less than 2 years. Now, we didn't do that. We just did the publishing. But then Artus and Boeing really did a lot of stuff to qualify it and everything, get it on the airplane in 2 years. It was military airplanes, so qualification was a little bit easier. But anyway, this is just last year finished by United Technologies. Again, similar idea or same idea, but using here two-stage topology with Vienna rectifier LC converter using silicon carbide devices in the gallium nitride on a secondary, and 98% efficiency. So this rectifier is 99, this converter is 99, the total together with the MI filters and the transformer 98. And that was the goal, to fit very small but have very low heat, because it goes in avionics base and they can't add any cooling. It just has to be natural in the avionics base, and that was the purpose of that one. So this could be done with silicon carbide. Now this is switching at 70 kilohertz, low frequency, because it's all about efficiency. Okay, towards the end, Boeing wanted to predict and do the trade-off the whole power system on the whole aircraft. So can you do it? Well, of course we can do it, but is it useful for anything? So, okay, we did it. We did the model for many, many, many components, and it's kind of very rough physical design, multidisciplinary. It takes mechanics, thermal, electrical, but very high level. And does some optimization, but mostly trade-off, not full optimization. And then, for example, this one calculates the total weight of the system, from the generator all the way feeder to the motors. And you can change specifications. For example, what is your generator frequency? What is the DC bus voltages you want to come up? What altitude you want because of the partial discharge and how much insulation and so forth. It was all calculated in there. And then you can go and change other parameters or change the description of the system with the DC. And when you do it for that sample system, you get, well, DC is lighter than AC. So let's build airplanes with a DC distribution, not AC distribution. You see you can save more than 10%. This is really good. Okay. Now we did it and tried to do it on some converters that were built according to our specifications, and our models for this converter that we built predicted the weight of 17 kilograms, and it ended up 24 kilograms. So you see, we saved, that system was 10% lighter, but our error is 30%. So don't trust what we say. So this is a tough problem. Everybody talks about global optimization. Extremely difficult. And if you don't spend more time on model validation and verification, then don't even do optimization. Okay. This is very difficult, very difficult. It's fun and great things, can publish a lot of papers. I will not build airplanes based on that. Okay. Another thing also was interesting, stability. When you put all these converters together, generator, many converters, maybe even connected the grid on your ground, you can get unstable because some impedance of a regulating converter on a DC bus could be negative, and because of this voltage divider, this could be -1. Something divided by 0 is not very good. Classical thing of instability because of negative impedance of regular converters. Also published almost 20 years by other people. Also, you can have it on AC buses, except the mathematics is a little bit more complicated. You do the matrix instead of just a scalar. And you can, that's a generalized Nyquist criterion, and you can do that. But Boeing was doing 787, and they were scared to that their system is unstable, and they didn't have any specs to give to suppliers what it should be so that it stays stable. And then they came up with the specs because they had smart people who knew this mathematics, came up with that and says, that's it. Okay, so then the supplier started supplying and says, okay, do you meet the spec, this impedances? And they say yes, and how do you know? Well, believe me. And says, why didn't you measure it? Well, there isn't an instrument in the world that measures it. There's just a theory. Okay, so then we got a project to come up with the instrument. So that's what we did actually. And this is a simulation. But you can show that there is negative impedance in one of the 4 impedances. When you have a 3-phase system, you have 3 impedance for 3 phases, but if it's a balanced system, you can transform it to 2. And then you can do it in rotating coordinates D and Q, and you really see negative impedance, some fixed value with minus 180 degrees, so that's negative number, and you can get instability. But what was interesting, when you look at the generator, for example, that one also has the output impedance, and that one can get negative here, if it tries to synchronize with the grid, and that's an interesting point. That never is shown in history, so that's something new. So we developed this box, which is this size, sits in Boeing, and then now they can measure the impedances of what suppliers deliver to them. And then in some of the systems, this is real. This was not measured in Boeing, this was measured in our lab. But when you have here a converter like AFE synchronizing with the generator and you connect it to grid and all 3 try to synchronize, what can happen is actually, this is the voltage at this point on the bus, not very high quality as you can see, but it's quite distorted by the current from this one. This active front end is not working, it's just a diode rectifier. So you see it has those blue currents pulsating. So, and then the current from this guy who supplies other loads is not so distorted, but distorts also the bus voltage. And then when we turn on the AFE, that's what happens. Oops. Yes, so you'll see now when AFE starts turning on, good, it takes full current, it's nice sinusoidal current, but look at the current from the generator current to AFE. Finally, they fall apart, they can't synchronize with each other. Because you have multiple PLLs and everybody's synchronizing with himself and with all the others. And they can't agree with whom to synchronize at the end. And, okay, you may tell them synchronize with that guy, but if I'm looking at the wire, how do you know who is that guy? Okay, so, okay. But that's what this impedances can predict probability of that happen. You actually can apply Nyquist, you can come up with specs so that when you put these known equipment together, you would know whether it will be stable or not. Okay, that's for big system integration. I'll skip now. Yes, when we build those little one systems, they do get unstable, and we've shown it many different ways. So that would complete my presentation. And it has been a great fun working on power electronics, especially hoping that we're doing something useful for the others. Thank you very much.